Okay, the second half of section 9.6 covers the root test. And the root test works very similar to the ratio test as far as the conclusions that we can draw based on a limit. Okay. Now in this case, so in the root test, the limit that we're taking is the limit as n goes to infinity of the nth root of the absolute value of the term of the series a sub n. Okay, so we have three parts to this test. So if this limit exists, this nth root of the absolute value of a sub n, if it exists and is equal to L, which is less than 1, then we can conclude that the series is absolutely convergent, which of course means that the series is convergent. Okay? The second part is that if this limit is equal to L and greater than 1, then the series is divergent, and if this limit equals 1, then the root test is inconclusive. So you can certainly see how this is very similar to the ratio test, other than we are taking a different kind of limit here. Okay, so in our first example, we're going to test the convergence of the series given here, where we have this fraction being raised to the nth power. And so whenever you see a series that looks very similar to this series here, that is some fraction ring raised to the nth power, it usually is going to require the ratio test. Okay, and so one thing to note before we actually apply the ratio test is that you might think, well, maybe we could compare this to the geometric series. Okay, notice that for large n, what's in parentheses is roughly 2/3. So, but if we wanted to compare to, let's say, the geometric series, where the ratio is 2/3, which we know would converge since 2/3 is less than 1, we can't quite get the inequality in the right direction. So let's just note that we cannot compare to the geometric series with ratio 2/3. So we'll just state that we cannot compare to a geometric series of ratio 2/3 since the inequality is just in the wrong direction. We would have that 2/3 is actually less than or equal to 2n plus 3 over 3n plus 2. Okay. Now we could possibly compare to a geometric series that has a larger ratio, but that setting up that inequality is a little hairy. This is really just a simple application of the root test. So we consider the limit of the nth root of this expression, of course an absolute value, which doesn't really matter in this case, is everything in the parentheses is always going to be positive. So that nth root cancels out the power raised to the n, so we get that we're just looking at the limit as n goes to infinity of 2n plus 3 divided by 3n plus 2. Very easy limit to compute. This limit is 2/3, which is less than 1. Therefore, this series converges absolutely, or as I'll just abbreviate as AC, absolutely convergent by the root test. Okay, so now as a second example, we're going to test the convergence of the series given here, where we have this expression 4n minus 1 divided by 3n plus 4 being raised to the nth power. And so here it's obvious. The root test is the way to go. Okay, and again, if we wanted to try to compare this to a geometric series, we would want to compare it to the geometric series of ratio 4/3. Okay, and we know that since 4/3 is greater than 1, that geometric series diverges. But if you try to set up the inequality in the way necessary to use direct comparison test, it would be in the wrong direction. And so I won't write out the details, but hopefully you can see that. Let's just go and actually compute the limit here. So we want to compute the limit as n goes to infinity of the nth root of the absolute value of a sub n. In this case, again, the nth root cancels out that power of n, so that we are simply looking to compute the limit of this expression 4n minus 1 over 3n plus 4. And of course, this limit's easy to compute. It is 4/3 greater than 1. Therefore, this series diverges by the root test. Okay, so we've looked at two pretty simple examples, and let's move on to something that was going to be a little bit different, that is still going to require the root test. Okay, so this example given here is a little bit different than the previous two. Basically, this quantity is now being raised to the n squared. Okay, but we can still use the root test. So to use the root test, we want to consider the limit as n goes to infinity of the nth root of our a sub n in absolute value. So now in this case, when we take the nth root of something that is being raised to the n squared, now we don't just get a canceling. We get some canceling, but we still have an n in the exponent, so we will have a limit of n over n plus 1 raised to the n power. Alright, so now, when we look at this limit, what we really have? Well, we really have 1, in parentheses, the expression in parentheses is going to 1, and of course n is going to infinity, so we have a 1 to the infinity indeterminate form. Okay, and so to deal with that, what we do is we convert this to, we take the natural log of both sides and then proceed to use L'Hopital's rule. Okay, and you can go through that exercise, but what I want to point out is, so let's note that if we look at the limit of the reciprocal of this guy, which is n plus 1 over n raised to the n power, which of course if we simplify the expression or modify it, that's in parentheses, we have a 1 plus 1 over n to the n power. And so what is this limit here? Well, this is a way of defining e. Alright, so the limit that we're actually interested in, what is the limit as n goes to infinity of n over n plus 1 raised to the n power? Well, it's just the reciprocal of the result that I have just noted. So it is 1 over e, which of course is less than 1. And so we can conclude by the root test that this series converges. And actually, it is absolutely convergent. So it's absolutely convergent by the root test.